Open with a direct, visual question. What if the place most like an alien ocean wasn't on Europa or Enceladus, but right under our feet? Show a descent from the light-filled surface into total darkness. Point out that, thousands of meters deep, the pressure can destroy cameras, robots, and vehicles in seconds. Introduce the central mystery. NASA isn't going down there to look for monsters, but to test how to explore worlds that might conceal oceans beneath kilometers of ice. The audience should feel that the Earth's abyss is a gateway to a larger question. Could life exist in an ocean without light? Explain that the deep ocean presents conditions similar to those expected on certain worlds in the solar system. Permanent darkness, extreme pressure, limited communication, unknown terrain, and the need for autonomous navigation. Therefore, the deep ocean serves as a natural laboratory for testing systems that could one day be used beyond Earth. The connection with NASA is not about a secret revelation, but rather about developing and testing technologies capable of operating where humans cannot easily do so. Simply put, before sending a robot into an alien ocean, you first have to prove that it can survive and navigate in the most challenging ocean on Earth. Recall the case of a deep-sea vehicle lost during a mission. Present it as a cautionary tale. Years of engineering can vanish in an instant when pressure exceeds a structure's limits. Maintain the tension with a question. If even one of the most advanced machines can be crushed without sending a final signal, how can you explore a territory that destroys its own explorers? Use this moment to dispel the notion that simply building a larger, more expensive submarine is enough. Explain the change in strategy. Instead of relying on a single, enormous, expensive, and irreplaceable vehicle, researchers began to favor more compact, modular, and reproducible platforms. If one unit fails, the entire mission doesn't have to end. This philosophy is similar to sending a fleet of small explorers instead of putting all your eggs in one basket. Present Orpheus as an example of this approach. A lightweight robot designed to explore great depths autonomously and with less financial risk. In other words, losing a small robot is a setback. Losing the only giant robot could spell the end of the whole project. Introduce the most compelling idea from the first part. How does a robot find its way when GPS doesn't penetrate the ocean? Describe Orpheus moving across a black landscape, without satellite signals and without a pilot monitoring every turn. Compare its situation to that of a traveler in a forest without a map, forced to recognize rocks, slopes, and terrain formations to avoid getting lost. Explain that the robot uses visual navigation and seabed feature recognition, technologies related to autonomous systems developed for space exploration. Instead of following a GPS signal, it creates references from the landscape. It identifies structures, compares images, and estimates its position. This autonomy is essential both in an ocean trench and on a distant world, where commands can take time to arrive and immediate human intervention is not possible. To put it simply, the robot doesn't ask where it is. It observes the terrain, remembers what it has seen, and calculates its own path. And this is just the beginning of the abyss. If you want to discover how life defies the rules in places where nothing should survive, like subscribe and turn on notifications, because what appears in the following depths changes our idea of a habitable planet. To demonstrate that the ocean floor is not an empty desert, but a set of ecosystems that function with different rules than those on the surface. But surviving the pressure wasn't the most surprising discovery. What was truly baffling was finding entire communities living without a single drop of sunlight. Before we continue, write in the comments what you find harder to believe. Life alongside superheated water or animals that have never seen the light of day. And leave a like if you enjoy mysteries explained with science. Present hydrothermal vents as fissures in the planet. Dark plumes spewing hot, mineral-laden fluids from the Earth's interior. Create a contrast between a seemingly deadly environment and the abundance of organisms surrounding it. Ask, how can a complete food chain exist in a place where no plants grow and where light never reaches? Introduce tubeworms, clams, crustaceans, and microorganisms as inhabitants of a biological city built around a toxic chimney. Explain chemosynthesis. Certain bacteria and archaea obtain energy from compounds like hydrogen sulfide and transform that chemical energy into organic matter. Other animals depend on these microbes, either by eating them or by hosting them within their tissues. The finding changed a long-held scientific view. A food web can begin with chemical reactions driven by geology. On the surface, life usually charges its batteries with light. In hydrothermal vents, certain microbes charge them with chemical substances that come out of the rocks. Bring the narrative closer to the organisms themselves. Describe blind shrimp clustered near hot vents, forced to remain within a narrow band. Too far means lack of food. Too close can mean lethal temperatures. Present a scene of extreme survival and a question. How does an animal without eyes know where to stop when the slightest movement can pull it into scorching water? Add that, in resource-scarce environments, some species may exhibit aggressive behavior or feed on their own kind, but avoid presenting this as a universal rule or as a deliberately monstrous colony. Explain that some deep-sea animals possess sensory organs adapted to detect heat, chemicals, vibrations, or changes in water flow. The absence of functional eyes does not mean an absence of perception. In a lightless environment, investing energy in vision may be less useful than developing sensors to locate food, avoid dangerous temperatures, or find mates. Being blind in the dark is not necessarily a disadvantage. These animals read the heat and chemistry of the water like we read signs on a road. Introduce brine pools as an impossible image, lakes with visible shores on the seabed. Show fish approaching a liquid surface denser than the surrounding water and ask, how can there be a lake beneath another lake? Highlight that these accumulations can contain so much salt and so little oxygen that entering them is deadly for many animals. Yet, right at their edges, communities of mussels, worms, and microbes appear. Explain that brine, due to its high salt concentration, is much denser and becomes trapped in depressions on the seabed, forming a visible separation. It can contain methane, sulfide, and other substances hostile to many life forms. Even so, specialized microorganisms utilize these compounds and sustain organisms associated with them. Reconnect with space exploration. Dark, saline, and chemically active liquid environments expand the list of places where life might be sought. It is an underwater lake because its water is so salty and heavy that it does not easily mix with the ocean that surrounds it. Up to this point, the lesson seemed clear: life could survive without light. But the next discovery was even more radical, because it wasn't on the seabed, but buried kilometers below the Earth's surface. To bring the mystery from deep-sea ecosystems to life buried under rock and show why this evidence changed the search for extraterrestrial life. If life can exist without the sun at the bottom of the sea, the next question is much more unsettling. How far can it go from the surface and still be alive? Comment right now where you think life is most likely to be found beyond Earth. Under the ice of Europa, beneath Mars, or in another distant ocean. Leave a like so more people can discover this part of our planet. Move the story from the ocean to a deep mine in South Africa. Narrate the discovery of microorganisms in water trapped within rock fractures, kilometers below the surface and seemingly isolated for immense periods. Pose the central question. If they receive no light, don't eat plants, and don't depend on the outside world, what keeps these organisms alive? Emphasize that they are not giant creatures, but life capable of persisting almost entirely separate from the surface biosphere. Explain that certain microbial communities can harness hydrogen and other products generated when natural radiation from rocks interacts with water. This energy sustains chemical reactions and allows them to maintain extremely slow metabolisms. Clarify that these organisms are not literally extraterrestrial. They are terrestrial life adapted to exceptional conditions. Their value lies in demonstrating that an ecosystem can depend on the energy of the rock, not on the climate, the atmosphere, or surface sunlight. Simply put, rocks release small amounts of chemical energy, and microbes survive by harnessing it for a very long time. The idea is that for a long time the search for life focused on surfaces, Martian landscapes, atmospheres, and areas where sunlight could reach. But the question is, what if the surface is precisely the worst place to look? It's important to remember that radiation, extreme cold, and the absence of a protective atmosphere can make a world's outer layers hostile, while the subsurface can retain heat, liquid water, and chemical reactions. Explain how Earth's deep ecosystems have expanded astrobiological targets. Mars could harbor niches within protected fractures. Europa and Enceladus could contain oceans beneath their icy crusts. And hydrothermal vents could provide chemical gradients useful for metabolism. Avoid claiming that life has already been found there. The correct conclusion is that potentially habitable environments exist and that Earth demonstrates that sunlight is not an absolute requirement for all life. We don't know if there is life beneath Mars or Europa. What we do know is that we can no longer rule it out just because those surfaces are dark, cold, or seemingly lifeless. Change scale and show astronauts entering an underwater habitat. Ask, why train for the Moon or Mars by living for several days under the ocean? Present the environment as an upside-down spacecraft. Instead of being surrounded by a vacuum, the crew is surrounded by water and pressure, but in both cases, going outside without protection can be fatal. The isolation, the confined spaces, and the dependence on technical systems make the underwater environment a psychological and operational test. Explain that analog underwater missions allow for practicing procedures, teamwork, limited communication, simulated extravehicular activities, and failure response. They don't replicate every detail of space, but they do force crews to work with discipline in a confined and hostile environment. Link this training to the central theme. The ocean not only helps us imagine where something might live beyond Earth, it also teaches humans how to explore those places. An underwater habitat serves as a test because it forces you to live inside a technological bubble, just like a space base. Up to that point, the ocean had already shown life fueled by rock, heat, and chemistry. Then the instruments detected something that seemed to break another fundamental rule: oxygen increasing in complete darkness. They opened sealed chambers placed on the Pacific seabed to measure how much oxygen organisms consumed. The prediction seemed obvious. Inside a sealed container, oxygen should gradually decrease. But some sensors recorded the opposite. The question arose, how can oxygen increase at almost 4 kilometers deep, with no light, no plants, and inside an isolated chamber? The researchers suspected a malfunction and repeated the measurements before considering other explanations. It should be clarified that the observation was described as the production of dark oxygen, but its mechanism still needs to be investigated and independently verified. Experiments suggested that the increase was not easily explained by photosynthesis or normal microbial activity. However, an unexpected reading alone does not constitute a definitive conclusion. The rigorous way to describe this is to distinguish 3 levels. The instruments recorded an increase, the researchers ruled out some simple explanations, and then they proposed an electrochemical hypothesis. What has been confirmed is that the measurements surprised scientists. What is still being studied is exactly what produced that oxygen. Focus your attention on polymetallic nodules, dark masses that grow very slowly around small fragments of the seabed and concentrate manganese, nickel, cobalt, and copper. Ask, what if these rocks weren't just mineral deposits, but a network of tiny natural batteries? The hypothesis is presented as follows. Certain voltage differences associated with the nodules could contribute to the separation of water molecules through electrochemical processes, releasing oxygen without photosynthesis. It is important to emphasize that this is a scientific interpretation under evaluation, not conclusive proof that all these rocks continuously produce oxygen. The result would be significant. If mineral processes can generate oxygen, then detecting it on another world would not, in itself, be sufficient to demonstrate the presence of organisms. The complete geological, chemical, and atmospheric context would need to be studied. An oxygen signal can have more than one origin. It can be related to life, but it could also arise from non-biological reactions. To conclude, consider a current conflict. The same nodules that are of interest for their battery metals could be part of slow and fragile ecosystems. Pose an uncomfortable question. What happens if we extract a resource on a large scale before understanding its function? Many structures and communities develop over enormous periods, so the damage could persist for generations. Explain that deep-sea mining raises ecological questions related to sediments, noise, habitat loss, and the disruption of communities that have not yet been fully described. Connect this caution to the entire journey. Hydrothermal vents demonstrated that life doesn't need light. Subterranean microbes showed that it can depend on rock. Brines revealed ecosystems in toxic waters, and nodules may be linked to unexpected chemical processes. The lesson isn't that NASA has found monsters or confirmed extraterrestrials, but that each dive reduces our certainty about where life might exist and what signs we should look for. The more we learn about the abyss, the more evident it becomes that it is not an empty space. It is a complex system that can teach us about Earth and other worlds. It ends by returning to the initial image, a robot moving alone through the background, barely illuminating a few meters. Perhaps the answer to whether we are alone will not come first from a telescope, but from a machine learning to recognize rocks in the dark. Because before we drill through Europa's ice or search for life beneath Mars, we must understand the alien world that already exists on our planet. If this trip changed the way you imagine the ocean, subscribe now, turn on notifications, and share the video. And tell us in the comments, do you think the first extraterrestrial life will be found underground, under ice, or in a distant ocean?